Arshdeep Singh, sir. Sir, am I audible, sir?
Yes, sir. Yes.
Yes, sir. Good afternoon, sir.
Good afternoon, sir. How are you?
Sir, myself, sir, Professor Praveen Bhojne from the MIT SUS, sir.
Hi, sir.
Sir, hello, sir. Sir, shall we start, sir? Either should wait for 2 or 5 minutes for candidates. We already
Yes,
put the message in the group.
I will start at 2:05.
Okay, sir.
We
Okay,
will
sir.
wait for two
Then we will
minutes
wait for
and
2 minutes. 2 minutes, sir. Okay,
yes,
okay, sir.
my
Okay.
screen is visible.
Yeah,
Can
yeah.
you
Your screen is
confirm that?
visible. Your screen is visible, sir.
Okay, okay, okay,
Yeah,
okay. Then I will start in 2 minutes.
yeah. Sure.
Welcome everyone. Uh, I hope I am audible and my screen is visible to everyone.
Yes, sir. You're audible and your screen is visible, sir.
Okay, okay. Thank you, sir. So, in the previous sessions, we have seen what ROS is, why we need, where does it fit into into the field of robotics. Then we seen about the Linux, about the Ubuntu, how graphical interface, how command line interface works. Then we seen the demonstration of the command line interface for the Linux. Then we moved to terminal PowerShell and that discussion. Then in the last session, we started the uh, basic command line introduction for the ROS2. And in that, we have seen the first basic command ROS2. Then we have seen package and node related commands, how to see node list, how to see node info, and also we installed two packages, TurtleSim and RQT, for demonstrating these basic concepts of ROS. So continuing that, I will today I will be demonstrating about the commands related to topics, services, parameters, and actions. So I will just first open the terminal and I will run the TurtleSim package, and from TurtleSim package I will run two nodes, one TurtleSim node and another teleop node, and I will just start the RQT graph so that we can see the nodes messages topics visually also. So So the first node of the turtle sim is just started. Let's also run the another node. So these two nodes are started. Let's see if uh, tally up node is working. I will just try to move the small turtle by giving command from my keyboard. And yeah, it is working. So let's just start the RQT graph node. So we already discussed about this RQT in the previous session. So the basic setup for the nodes and the packages we have been discussed in the previous session. So let's start from the topics. We already know what topic is, how it enables communication between the nodes. So let's see the basic commands related to topics available in the ROS2 command line. So the basic command is topic and the sub commands are listed here to echo, to find, to list the topics. We use these commands because we want to know what type of message, what type here means what data type, what data structure is being transmitted or being communicated via messages on the topics. So uh, every topic has an particular type of data structure and we can transmit messages by abiding to that particular data structure only, and that data structure is designed by uh, ourselves only. We have freedom. We can like make combination of any sort of data type like string, like integer, float, double, anything we can want. We can just have to make that type of message structure, and we have to define that while we are writing our publisher or subscribers. So as I have already started the notes, let's check what these commands return one by one. Apart from the topic command, the another useful command for seeing the structure of the message will be interface. So first just let's check the topic list. So these five topics are currently active and the nodes will be communicating on these three topics. So we got the list of the topics. Now, how to know what a particular topic holds? We need more information about that topic. For that, we have command of info. Let's just check what does this topic turtle1 pose has. For that, I am just going to type ROS2 topic info and my topic name. You can see it is giving output on the terminal. The first is type. This is the type of the message that is being transmitted on this topic. Then it is saying there is no subscriber on this topic and only one publisher is present on this topic. So we got the list of the topics, we got the information about the topic, means how many publishers it has, how many subscribers it has, and what type of message it is publishing or subscribing. Now we want to know what this type of message holds. what data type it has, so that we can, if we want to publish, we want to subscribe, or we want to change something, we we should have information that what type of what structure type is being used for the communication. So for that, there is a command ROS2 interface show, and we want to know about this type of message. So just a minute. ROS2 interface help. Let's see what does it holds. So it has similarly list packages and show. So let's see what type of messages are currently being active by just running these two petrol sim nodes. So currently it is showing all the type of messages that has been used on this system. As I am a frequent user, so I have long list of messages. You can see for every package, like it is an SLAM package, you can see a single package holds multiple types of messages. So these are user defined and modular as per our need. So we there is like nothing binding us to define our message type. If we want that only just integer data should be communicated, then only one integer data will be communicated. So let's see what it actually look like on the command line interface. ROS2 interface. So show is helpful for outputting the interface definition. Oh, and our message type was this sim message pose. Let's see what it holds. You can see it is outputting 5 lines. First, there are 5 variables x, y, theta, linear velocity, angular velocity, and each has type of float 32-bit. So this is defined by the developers of the package. If we are developing our package, we can uh, define our custom type of message. Now, we have seen the list of the messages, how to know what type of message is being communicated and what is its structure. Now, we want to see actually how data is being communicated. Means here we are just getting the name of the variables, but we want to know at this particular time instance what value x holds, what value y holds, what value theta holds. For that, there is a command echo. So we will be using that command ROS2 topic echo and our topic name. Just first list the topics so it becomes easy. ROS2 topic echo, and we want to see what does this turtle1 pose topic is communicating in actual values. You can see it is continuously being published because the nodes are running and it is using the simulation time, and data is being published as per the frequency set, and it is usually 1 Hz. So you can see we got all the 5 variables, and what we are getting a particular value for these variables. As it was a pose message, so it is supposed to hold the orientation of our turtle. So it is holding some coordinates for x, some coordinates for y. Similarly, an orientation theta, then its angular velocity. So now let's using the tally of node, let's just move the turtle to some other place. Then we will again echo the topic and we'll see how data has been changed. So now let's again try to echo the data of the topic, and there is one sub command. Once, if we want to publish only one instance of the data, because it is being continuously uh, transmitted, so if we want add only one instance data, we will use one sub command, and you can see at the last time the x position was 5.5 and now it is 7.2. Similarly, there is change in the y. Similarly, there is change in the theta. As it is stopped, turtle is not moving, there is no velocity. So in this way, we can interpret the topics by listing them, by echoing them, by knowing what type of data they are communicating, and we can actually see that data. Now, as the echo command is just showing the results on on this terminal only. If we want to just get the data and we want to see it later, then we must store this data into a file. So how do we store this data into a file? So first just move into another directory where we want to save our data of that particular topic. We will be using same echo command but with directives. I have discussed about directive in previous session also. If you remember, to save information in the file, so I will using this directive and I am want to save this data into file name data.txt. So we are familiar with this command till this. It will be publishing, it will be outputting the data on the terminal. Now we are using this directive. This directive will take the output of this command as input and will store the output of the command into this file. Let's just run. As all the output is being stored into the file, so it is nothing showing on the terminal. Let's just uh, now let's just see what data.txt file holds. You can see it has x, y, theta, and as we are not moving the turtle, the same data is being stored in the file as there is no movement, nothing is changing, and we can, if there was some changes like the turtle was moving, then we can see that data just by storing into the file. So apart from that, there are 2-3 more commands related to topics that are helpful. One is hertz and another is pub. pub. So like there are two ways. One is moving the turtle using this tally-op command by typing on my keyboard. Another is as there is a topic which has the pose of the turtle, and there is another topic which has velocity of the turtle. So if I just publish some data on the topic which is related to the command velocity, so I can move my turtle. I can just give some velocity to the turtle from using this publish. So publish, while publishing, as we are publishing a message, and we already seen that message has a particular type of data structure and we need to abide that data structure while publishing. So let's just check what type of message this command velocity topic has and what is its data structure. So for that, ROS to topic info for knowing the information about the publisher, subscriber, and the type of data that has been communicated on this particular topic. You can see there is one subscriber, one publisher on this topic. Let's see from the RQT how does it look like. So you can see this is the command velocity topic and there is only one publisher on this topic and there is one subscriber on this topic. So this tally of node is publishing data as I'm just giving commands on the keyboard. So that data is being published through this topic to the turtle sim which is receiving the commands and doing some motion. So we got the type of message. Let's see what is its data structure using ROS2 interface show and type of message. You can see it has two vectors, one linear, one angular, and having a float 64 data type for all its variable as it is a topic for the velocity. So there is two components, linear and angular, and in all three coordinates x, y, z. Now for publishing, let's just move to documentation for little help because we will are not going to remember how to publish some data. So you can see here for publishing data, they are using topic, then message type, then the actual data they want to publish on that topic. And you can see there is linear and angular two components, then each component holds x, y, z, x, y, z. So we need to take care of this factor, like if there are variables named, like there are two variables x and y, so we have to mention the data for each variable while publishing. So let's just copy this command and try to publish the given command velocity on this topic and we'll see the result on turtle. You can see it just started moving around in circle. So what data we gave? We gave it an angular velocity about the z-axis. Basically we give it yaw rate and then an angular velocity. You can see here there is an angular velocity component about z is 1.8, then there is an component about x for the linear velocity. So this way we can publish the data on the topics. So apart from the topics, we have services, parameters, and actions. So as we have seen commands about the nodes, topics, and how to know what type of message is being published or subscribed. Similarly, for services, service server and server client, action server and action client, we need to abide the rule of the messy data structure. And for services, we define our structure with the format of .srv, and similarly for actions. So as we have just seen how we can know what data is being communicated, what data structure we have to abide. So this similarly applies for services and actions. So let's see what does ROS offers for services. For that, ROS to service and help. So it has basically four commands, four sub commands for services: for calling a service, for finding a list of available services, and then type of service. So let's just run ROS to service list so that we can see which services are available by running these two nodes. You can see there are multiple services available. Some are related to Turtle Sim node, some are related to Teleop node, and others are for the RQT node. So how we can call an service? What we have studied about the service is that there will be a client, there will be a server. Client will be asking for some data and server will be providing that data, and there is no feedback. Client will wait until the server provides the data. So let's just see how to call a service. ROS to service call help. So we can see what arguments we need to pass. So it needs three positional arguments after the service call: service name, service type, and values. We got the service name here from the list. Now we need to know the service type. And service type is basically like we have seen the topic type, means what type of message is being published. So let's see. For this spawn service, let's just see what type this service has. For that, we already have the command of type, and let's just check the type of the ROS to service type for spawn. We got this is the type of message being used by this spawn service. Let's check what does it holds. ROS to interface show and turtle sim SRV spawn. As I already told, for services we use the SRV format. So it holds float type of data, then string type of data. So it has the position in XY coordinates and an orientation about the Z coordinate, and a string name which they are saying optional. A unique will be created, unique name will be created and returned if this is empty. So what does this service do? As there is only one turtle now, so spawn is basically getting more turtles here. If I want to add a new turtle, then I can use this spawn service, and it offers me to decide the name of the turtle and the position and orientation of the turtle I want to, at which pose I want the new turtle to be. So we have seen the list of the services, how to see type of the services, and how to see what data structure that type of service holds. Now we move to call and service, and we have seen service name, service type, and values. So for values, we will be using this as we just published a message and we have to follow an particular structure. For similarly, for calling a service, we the need to pass the arguments in this manner only. So let's call this spawn service ROS to call. Now first argument is service name, that is ROS to service call. First is name of the service, which is spawn. Then we need service type, and which we have just seen using the type command itself. Now we need to publish. Now we need to basically pass arguments, pass values for x, y, theta and name of the turtle. If you are not able or gets confused how to pass these arguments, you can always refer to the official document. There you will get one, two examples, so you can understand how they are passing the arguments for calling the service. So you can see here they are using this. You can see they have just assigning the values for the x, y, theta and name. So let's just use this and see if we get a new turtle or not. So they have not mentioned the name of the turtle, so I will just give it some name, me. So let's just call this service, and you can see in output what we are getting. We are getting a requester and a response. Requester means a service client is making a request to this service to spawn an turtle at these coordinates with these orientation named me, and in response that service is responding that it has spawned a turtle named me. Let's check if it is spawned or not. You can see first there was only this turtle, now there are two turtles. So now let's see if there is any change on the node list. Let's just first see graphically and refresh this RQT. You can see there is no change in the nodes, and it has been verified from graphical uh, interface also, as after refreshing there is no changes. So the turtle has been spawned, but no new node is created. It is using this turtle sim node only. So let's call another service also, which is to clear this, as it has a path that it followed till now. If we want to clear it, we can use the service clear. For that, let's just see the service list which we have, and there is a service named clear. Now let's see ROS to service type clear. So this is the type of message that clear service has. Now let's see what arguments we will need to pass for calling this service. So it has no data. We need to pass no data for calling this service. So just call this service ROS to service call. What were the arguments? The first was the service name, which is clear, and another was the type of the service. You can see the similar sort of output for requester and response is being showing, and let's see if the traced path has been cleared or not. You can see the path has cleared. There is means service work. So this is about the services. Now we have not discussed about the parameters, but if you have some background with the programming, you can understand that parameters are just the values that a user can change at the runtime. Like if I have this node running and I want to change something about this node is outputting a graphical interface. So like if I want to change the background color, so it is upon the designer and the developer of the node if he wants to give access to the users that they can change these things at the runtime of the node, or like at the runtime means just at the time of calling the node or when the node is running. For that there are parameters. So let's see if ROS2 offers something related to parameters. And you can see there is a command which holds subcommands related to parameters. So let's see what does it has to offer. So parameter command holds multiple subcommands for setting the parameter, getting the parameter list, for description of the parameters, for saving the parameters into a file and getting parameters from that file. So we will see basic two or three subcommands related to parameters. So first we will see the list subcommand to get the list of the parameters that are available. So you can see for each node there are list of parameters, and I just described about the color of this turtle sim node, and the developer has provided the option to change the background color of this node. So by using this parameter I can change this color without shutting down the node or making changes in the code. So I am going to make changes while a node is running. So now we got the name of the parameters. Now we need to see what value we need to how to set value, or what current value this parameter has. Let's see, we want to see this for this background underscore b parameter. So for that we will be using this get parameter command to see what value this parameter currently holds. Get, and we can also use help to see what it needs. So it needs two positional arguments, node name and parameter name. So we just have to pass two arguments, the node for which we are seeing the arguments and what particular parameter we want to know. For that, ROS2 param node name is turtle sim. Now the parameter name, which is background underscore b. Sorry, there is one subcommand is missing, get. So you can see currently the background b is set to 2 to 5. Now I want to change it. I want to set it to 0. For setting the parameter, there is subcommand set. For getting the value, the subcommand is get, and for setting the parameter, subcommand is get set. ROS2 param set, following the same syntax. First node name, then the parameter name. Now let's see how to pass value. For that we can use help, and it is saying that it needs three positional arguments: node name, parameter name, and value. So let's just pass a value of 0, as it needs an integer value and 0 is an integer. So you can see that we are getting the output that set parameter successful, and you can see the color of this turtle sim background has been changed. So this is about the parameters, how we can make changes at the runtime while a node is running. So we have seen services, topics, nodes, parameters, message types. So now only one important thing is remaining, that is actions. So let's see what does ROS2 has for actions. Let's see, is there any command for action? Yes, you can see there is an action subcommand. Let's see what it holds. ROS2 action help. Am I audible? I think there is some
Yes, sir,
internet
you're
issue
audible, sir.
from my side.
You're audible, sir.
Okay, okay, thank you. So, yes, I was discussing about this actions. So let's see what actions we have by running these two nodes. So you can see there are two actions available, and you can see one is related to turtle1 that we get when we just started the node. Then there is another turtle available that I named me. So we have two actions named rotate absolute for two turtles. So let's see, does this action list has some other subcommands? Yes, you can see it has three options. One is for help, one is count actions, and another is for showing the type of the action. For services, for messages, there was a particular subcommand type, but for this actions, it is being under the list command. So we'll see for this action what type of it has, and by type means what data structure will be used for communication by these action server and clients. ROS2 action, list, and type. You can see for both the actions we are getting the type of the action. Now let's just check info command, what does it gives for an action. ROS2 action info, and let's check for the turtle1 rotate absolute action. You can see it has one action client tally of turtle and one action server turtle sim. So here what does client do? Client requests and server responds. So this tally of turtle that was this particular node that we were just running to move the turtle is acting as the client here, and it is requesting output from the turtle. So this is input and turtle is acting as an output. So we have seen the action info, action list, and there is another option, send goal. As while describing the actions, I said it is mainly used for the navigation tasks which run for long durations, for which we need feedback that if there is any obstacle in the midway, or is there any change, or the robot is stuck. So we will just give some goal to this turtle and it will go there. So let's see what we need for using this send goal command. ROS to action, send goal, and help. So it needs three positional arguments: action name, action type, and goal. We already get action name and action type. Let's just use them. ROS to action, send goal. First is action name, which will be turtle1 rotate absolute, and action type, which we just get from using the list command with the sub command of type ROS to action, send goal, turtle1 rotate absolute. This is the name of the action. Now type of message, type of the action. Now there is only one argument remaining, that is goal. So how we know what we need to pass in the goal, or what it allow us to pass? For that we need to see what data structure it holds. So for that we need to pass the type of the action to this interface show command, and you can see it has three options of providing a theta for heading direction in radians, then there is angular displacement in radians, and there is a remaining rotation in radians. So let's just change the heading direction by giving it some value. So let's just pass 1.57, means 90 degree. So what we are getting, fail to populate message fields, type error. So basically it is not matching with the predefined message structure. So as I earlier said, if we face some issues, we already have an official documentation which we can refer to understand what we are doing wrong and get some information. So what we have done wrong here, we have just passed the value and we forget that there are three variables and we need to provide value to that particular variable. So let's just use the variable name and the syntax provided, and let's see if that works, or still there is an issue. Still there is an issue because there is some typing mistake, and using the command line interface, you will often came across these issues of some small typing mistakes. Still, there is an issue. Let's just refer to the official documentation and see we are not using the correct syntax for defining the send goal data, because you can see there are two differences. One is the space between this theta and the numeric value, and in using ROS you have to take care of these spaces very clearly, because it is command line and with space things change. So you have to look for these small things. If you are getting an error and you are thinking that I am just following the things correctly, but there are some small things that we need to take care while using command line interface. And let's just run it. You can see the first thing is waiting for an action server to become available, then it is sending goal, then there is a response from the server which was not available in the services. Services was just was waiting until the result has came. Now it is server is first responding with an feedback that I got this, then the server is responding with the result, and this is the output from the node that the work you have given me has been done successfully. Now let's see if there has been some orientation change in turtle sim 1, this blue one. Now let's just give it goal one more time to observe if the orientation of this turtle one changes or not. So let's just give it again, and I think it is not visible, but it is. You can see it also gives us the final output, means the current orientation of the turtle, which is the result of our input. So this is about the actions. We have seen about services, topics, actions, parameters. So this covers the major portion for the basic command line related to ROS2. So if you have any query about the ROS2 command line, then you can ask now. And I already shared this official documentation in the previous sessions. If you have any issue, you can refer to this documentation. So this has some portions that I must tell you. One is a tutorial in which we the first one is command line tools that we have just discussed. So it just introduces to the available commands and how to use them. And for concepts, there is another section named concepts, and they divided into basic, intermediate, and advanced concepts. And like if you want to know more about the parameter section services, like just see about services, then you can get more information from the developers, like like how they work, and you can like get little bit more information if you need more understanding. And another way is to, if you are good with programming and you can understand the programs, then you can go to their GitHub and you can see their source code, how actually they are implementing these concepts. So if you have any query on today's session or the previous session on the ROS2 command line, uh, then you must ask. So, is there any query?
Uh, Thank you very much, Dr. Arshdeep Singh, sir, for sharing your
Yes, sir.
valuable insights and rich experience with us today. So, sir, is there any query from the candidate sides or some? Okay, I think, sir, there is no query, sir.
Okay, so in the
Yeah.
next session tomorrow, we will be moving with the simulations. Uh, how does simulation, we do simulation in robotics, and I will be introducing one popular simulator also, and we'll see how we can use it with the ROS and what it basically offers, and we'll be demonstrating little bit uh, about it, like how to approach robotic simulations. So I think that's all for today's session, and thank you everyone for joining. So we will meet tomorrow for the this ROS2 simulations, and we'll be discussing briefly about Gazebo, its installation, why we need simulations, and its basic command line tools, and another things like that we need to know if we are going to start with Gazebo for simulations. So thank you, sir.
Sir, thank you, sir. Thank you very much. On behalf of the organizing team and all participants, we express our sincere gratitude for taking the time to be with us and making this FDP session so meaningful. Thank you once again, sir. Thank you very much.
Thank you, sir, for the opportunity. It was nice for me also.
Yes, sir. Thank you. Participants, there is a one feedback link in the your chat box. Just fill that form. Dear participants, there's a one feedback form in the link. Kindly fill it. Thank you. Thank you very much.
Yeah, dear participants, do not leave the meeting. So we have another session. You can take 5 minutes break.
क्या बोलते हैं वो? आई विल लेट यू नो सर। प्रतीक सर, आर यू देयर?
Yes, sir. Yes.
Mayur, I am here. So you can.
Sir, Shantakumar, sir, good afternoon, sir. It's Professor Praveen Vojne.
Yeah, good afternoon.
Sir, good afternoon, sir.
Yeah.
Uh, Sir, can we start, sir?
Yes,
Actually,
yes.
I think there are 70 participants are there, and then I think we have to wait 1 or 2 minutes, sir.
Yeah, no issues. Whenever you say
Yeah.
start, I already
Yes, yes.
share the screen, so we can start. No.
Yes, sir. So within 1 or 2 minutes, we will start, sir.
Yeah, no issues. No issues, please.
Yes. Thank you.
Yeah.
I think we'll start, sir. Sir, am I audible to you, sir?
Yes,
Shantanu,
yes.
sir?
Very much. Very
Shantakumar,
much.
sir? Okay.
Yeah. I can
So
start.
good afternoon, everyone. It's my pleasure to welcome Dr. Shantakumar Mohan, sir. He's professor in the IIT Palakkad as today's distinguished speaker. Dr. Mohan holds a PhD in robotics and control from the IIT Madras and extensive
Professor
academic
Praveen,
and research experience at institutions such as NIT, KST South Korea, and IIT Indore, sir. So we are truly honored, sir, to have him with us today. So over to you, sir, Dr. Santakumar Mohan, sir.
yes, yes, yes. I can
Yes,
start. No problem. Yeah.
yes, sir.
So I hope we left the last session on mechanics at this point, where we started talking about two body, how we can relate one information to another, mainly the positional and orientational information. There we started talking about description of position and description of orientation. The description of position is just a simple vector, whereas description of orientation is in the form of matrix. So that is what we have seen, and this is the last slide. I hope you all remember. So mapping between two frame. So where Q is the position. For this also we have given example. For example, Rolls-Royce car, the logo would be in the front. I want to know where the logo, but I always know that the logo is located from the car. Now, if I know the car position and orientation, I can always find the logo. That is the part we left. And and this is the relation which we got it. For example, this is the positional information of B with respect to A, and this is the orientational information of B with respect to A. This is what we call rotation matrix, and this is the position vector. So now, for example, if you look at it this, so this is a 3 cross 1, and this is 3 cross 3, and this is 3 cross 1 again. So here you see that the operation is heterogeneous. What that means, there is a multiplication and addition, and the nature of the system also you can see this is a 3 cross 1 vector and this is 3 cross 3 matrix. So people wanted to talk about homogeneous. So here I always give a very stupid example. For example, you take a class. In the class you have you can say girls and boys, right? So now if I say girls and boys, the class would be heterogeneous. So instead of that, if I call students, so then it would be homogeneous, right? The same scenario, can I actually like make it a homogeneous form? There only we are bringing one form called transformation matrix. So what that means, one frame to another frame information we are transforming. So that's what the transformation, and this transformation would be homogeneous so that we can actually like a generic. So indirectly, we keep it as a briefcase. Inside the briefcase, there is a position vector and rotation matrix. But if I call it as a simple briefcase, that is a transformation matrix. So if I keep a briefcase, so you have 10 classes. So you want to know what individual girls and boys in each class you want to know. So you can see that the 10 boxes, you pick which class you want to know, you pick it and see. The same way, the transformation matrix also, like you want to know how the transformation is inside, you open. Otherwise, it is just a case. So like a box or like a, you can say a briefcase. So that is what we want to know. If I put that way, so we need to see how to make a homogeneous, because here the matrix is 3 cross 3 and this is 3 cross 1. So in that sense, if I make it either 4 cross 3 or 3 cross 4, still I will not get kind of flexibility. What flexibility? If it is a matrix, that matrix as a square, I have always lot of advantage. If the square matrix is easily invertible, easily actually like manipulable, and we can actually like play as a briefcase conveniently. But if I actually like merge this position vector and the orientation vector as 3 cross 4 or 4 cross 3, that will not give that compatibility, right? So that's why we brought one addition, what we call the transformation matrix, that to like we are trying to bring it in a homogeneous form. So if I think about homogeneous, what we are trying to bring it, so instead of 3 cross 4 or 4 cross 3, we are making it 4 cross 4. So now if I am making it 4 cross 4, then what I will do the last row, right? So that is the bigger concern. So now if I actually like bring it the last row, you can see that I brought eta and sigma. So now the rotation matrix we always see in an orthogonal way. But imagine your camera is, instead of vertically projected, the camera is tilted. What will happen like our eyes? It will give a perspective view. So in order to bring the perspective, so you can make the perspective would be having only two angles. The camera roll angle will not make any change in the image, but the camera pitch angle and the yaw angle, indirectly the rotation about Z and rotation about Y will have influence that can be captured into 3 cross 1 vector. That is what we call perspective. That perspective vector we are putting it here as 1 cross 3. Okay. And apart from that, the position can be realized in a different way. For example, the position I can realize in number of pixel. So probably one of you may be realized in terms of inches, one will be realized in centimeter, one will be realized in meter. But I want to make it standardized. What I can do, I say that I want to use SI unit, everything in meter. Then number of pixel equivalent to meter, I can make it as a scaling. Number of inches to, you can say meter, I can make it as scaling. So that scaling what we brought it here as a scaling factor. So now you see that the complex process, which is heterogeneous, the position vector and rotation matrix, this I am actually like making it as a single transformation matrix. So this single transformation matrix is going to be 4 cross 4 and it is going to be homogeneous. So that is what we are going to use. Why? I already said we want to make it a compact form and we can actually like play as an operator. If I want to play as an operator, then I should have a square that too homogeneous in nature. That is where we brought it. Now you can see that in that scenario, the homogeneous transformation matrix consists of two operations. One is position, another one is rotation. The original transformation matrix, what we brought as, so the rotation matrix and position vector, right? The operation is done like this. So the rotation first with the fixed axis, then the translation next. So that's why we pre-multiply. This is what we supposed to do. But if you do the other way around, so you know matrix multiplication is not commutable, right? So the reverse of A cross B is not B cross A. So the same philosophy we brought it here. So that means this is what the original homogeneous transformation matrix, which we are doing it. If I brought transformation matrix, what advantage I will do? I'll get composite transformation easily. For example, I have transformation between A, B, C. I want to know. If I know transformation matrix of B with respect to A, transformation matrix C with respect to B, I just multiply these two matrices, I will get transformation matrix of C with respect to A. So that is what we can see, or any other form. Okay, so this commutation I can do, or this transformation I can do. So this is one important entity, because when I say manipulator, that is multi-body. If I say multi-body, so then there is number of frames would be, each body would be associated. Then I will be moving one body to another body. Then if I have a compound transformation, I can play from base to end very conveniently. That is the idea. So this idea you can actually like understand. The same way what we can do, second important thing, we can do matrix inverse. For example, I know the information of transformation matrix of B with respect to A. Now I want to know transformation matrix of A with respect to B. Earlier rotation matrix just a transpose, right? But the transformation matrix is not just a transpose. So we need to invert. That inverse also like quite easy. Okay. So if I make it these two product, that product supposed to be a identity matrix of 4 cross 4. So if I put that logic, I can find the transformation matrix inverse in this form X and Y. This X and Y also I can do it with the consideration like this. Then you can see that X would be just transformations like a rotation matrix transpose, and Y would be rotation matrix transpose multiply with the position vector, and it would be in opposite direction, so negative sign will come. So that is what you can see here. So this is the position vector transformation, which is indirectly inverse, and this is actually like this. Very simple to understand. For example, now I'm looking at probably 10-meter forward. Okay. So I'm saying that my laptop is, you can say 30 centimeter in front. Okay. Now the laptop is asking where is Shantakumar. Say that minus 30 centimeter in x-axis, right? So earlier I said 30 centimeter in forward. Now this is actually like reverse, because we are always assuming that the transformation like x-axis is forward. So that means this is actually like opposite direction of that. So the same logic it is here. And you can see like here, both axes are, you can say parallel. You can directly say it is minus 30, right? But imagine this guy is actually like rotated 90-degree. I'm actually like looking at, then I have to make it that rotation, say that. So in x-axis, I calculated for him, probably it is y-axis, right? Because 90-degree rotation. So that rotation only we are trying to do it. Okay. The same logic apply here. So now what we have done since yesterday we were discussing why mechanics, because we want to develop a real platform. We want to control the real platform. We want to actually like navigate or manipulate, or you can say play the robot. So then we need to understand the mechanics for betterment, right? So when I say understanding, there are two parts I already said. One is structural part, the other one is motion part. For that motion part, if we start, the motion is can be considered as combination of position and orientation change of position and orientation. Indirectly, we say change of pose. That is what we call motion, right? So then when we try to understand the motion, what we started, we said we describe the position, describe the orientation. Then we can see mapping between one frame to another frame. Now this mapping, we have come up with a compact form of transformation matrix. So I hope now you understood this. And the same way you recall, we said robot kinematics is mapping between two spaces. So when you talk about robot manipulator, mapping between the end effector usable, you can say space to the individual joint space. So what you call robot kinematics. For example, you know the joint variable, you want to find how the task variable located. So that is what you call forward kinematics. Whereas the other way around, you want to position and orient your end effector in some form. What would be your individual joint rotations or joint translation? That is what you call inverse kinematics. I hope you are clear about this part. Now we go little forward. Okay. So what we see little forward. So now I want to find out this transformation matrix for multi-body system like a manipulator, right? So when I see manipulator, what would be a bigger concern will come. So the bigger concern is n number of body and n number of, you can say, space. Each body to body, as per this understanding, you can see the position vector would be consist of three variable, and this rotation matrix consists of 3 variable. Although it would be 9 element, but you can say independent elements would be, or independent variable would be only 3 rotations. So that means one body to another body to describe, you need 3 orientation and 3 translation, indirectly 6 variable required, right? And when you talk about manipulator, so the manipulator, you can see that the active joints indirectly, for example, I take my arm from shoulder to my wrist. So it is having a 7 joints, right? So shoulder has a cup joint, which has a 3 rotations, and elbow has 1 rotation, and wrist has again a ball joint, so 3 rotations. So totally 7 rotation is possible, right? But now imagine one body to another body. If I want to describe, I need 6 variable. So then you can see if I include ground and include the tool tip. For example, I have a drill bit. The drill bit tool end is actually like attached on the workpiece. The other end is attached on the rotating base. So now when you talk about the joint ended at rotating base itself. But you want to know where the tip. So that means you need to have, so not only the number of body frames, you have a base, one more addition frame, and tool tip is another frame. So indirectly, you have n bodies or n joints. So you have n plus 2 frames required. So in that sense, how many variable to describe? 6 times of n plus 2. So that means 6 multiply with n plus 2 times. So for example, I have 2 body or 2 joints. So 6 into 4, I need to have 24 variables. So then it is very complex, right? So and when you go this rotation matrix, the rotation matrix doesn't have a straightforward orientational information. I want to find out what would be the roll angle, what would be the pitch angle, what would be the yaw angle. I cannot find directly. I have to manipulate and get it. So that means I have a composite rotation which is not straightforward, and I need to reduce the number of variable. Can I reduce? So that is a bigger question. When the robot or robotic system has come, people brought in, then one of the popular approach was there. There are many approaches. So one of the popular approach brought by the 2 scientists or 2 physicists called Danawit and Hartenberg. So they brought some kind of approach called Danawit-Hartenberg. So this approach bring it much simplified scenario. That is what you would have seen in robot manipulator or introduction to robotics course, or even when you create a URDF, you may be using this parameter, kinematic parameter, right? So that is what we are trying to understand, right? So one body to another body you want to relate. So you need a 6 variable. Instead of that, can I make it simplified where I can see the joint, you can say translation or rotation, very convenient way. That is the idea. If I put that way, first big concern is where to put our coordinate system. Okay. And choice of coordinate, we have already decided Cartesian coordinate, but where to locate? That is a bigger question, right? When we do classical mechanics or general engineering mechanics, where we usually keep the body, or you can say coordinate frame, exactly the CG of the body, right? But when I keep the CG, so then what happened? The individual position to other position may not be easy to find. For example, one body connected with another body, the joint is need not to be located in a CG. Then I need to make another transformation. So in that concern, so Danawit Attenberg brought in that you keep your coordinate frame instead of you can say body frame, you keep it on the joint. Where you are locating your joint, there you keep it your coordinate frame. That is much easiest, right? So that is what one. And second thing is number of parameter, right? So they want to reduce. How they reduce? So indirectly, like what we are trying to see, the constraint is nothing but joints. So we are choosing the coordinate frame location as the location of the constraint or the joints. So that is one important thing we brought in. So then I already said, if I have n degree of freedom spatial linkage, then I would be having plus 2 frames, which is including base and end effector, right? So that means I need to have this many times of 6 multiplication would be the number of parameter. This is very different, right? And apart from that, there is no straightforward technique to mention the orientation of each frame. And the orientation of each frame I can represent in moving frame methodology, or you can say angle axis theorem, or Euler angles. Like that I can keep putting it. So instead of going away from this, in a simpler way, the Danavet-Attenborough brought some approach. What they did this convention mainly to bring it for a serious a spatial mechanism they brought in 1955. Later on, it published in ASME journal also. Okay. So what they said, that they said only 4 kinematic parameter required. That 4 kinematic parameter also very simple in logic. What they said, so each body, okay, can be connected with 2 joints, or each joint can be connected with 2 bodies. So in that sense, so one body to another body information can be brought it in joint. So that would be one displacement, one translation. The same way each joints, like there are 2 joints, each joint from another joint is displaced and oriented. So that means, so we can keep it only 4 parameters, which is we call kinematic parameters, are sufficient. But it is not that easy to describe, right? For example, if I take a ball joint, so that has a 3 rotations, right? So then these people thought what can be done. So they have done some crude way, but that is what better later on. So they said that one set of transformation to associated with the joint, another set is associated with link. So link parameter and joint parameter, 2 link parameter, 2 joint parameters, totally 4. That is what they brought. But for understanding this, so they brought some kind of conditions. What condition they put it? So each link, for example, you call body, right? That body is binary in nature. So indirectly, I call a link that is a binary link. So many of you may be mechanical. Binary link means, so this link can connected with the 2 additional body. Indirectly, this body can have 2 joints its own. Okay. For example, I can take a duster. This duster can be connected with the 2 other bodies. So that is what we call binary link. So beyond this, you cannot attach any more links. So that is one condition. Second thing is one joint, okay, can connect it with the 2 bodies. That is, we agree. But this joint can allow only one motion. So indirectly, I have 2 duster connected with 1 pin. This pin can allow to translate along with the pin, like you can say a translational joint, or it can allow only rotation about each other. So that means, so they said that single degree of freedom joint. So if this implies, so if I say robotic manipulator, the joint can be either rotary joint or translation joint. So then you may ask a question, sir, if it is a universal joint, or if it is a cylindrical joint, or if it is a spherical joint or a planar joint, how to describe? I have to consider, so 3 1D of joints. For example, I have a cylindrical joint. So the translation, I have to take it separate, rotation, I have to separate. For example, I have a universal joint. So 2 rotation, I have to consider 2 different joints. I have to consider as a virtual link. Although the link doesn't have mass or anything, but I have to create a virtual link. So that is the idea brought by Danavet-Attenborough. So now you can see that they put a condition. So any link you take it that can connect with only 2 joints. So indirectly it can connect with the 2 bodies. If I say any joint that can allow only one relative, you can say motion, either it is a translation or rotation. So that is the condition. In that sense, you can see that I can easily apply the 4 kinematic parameter. Furthermore, they want to imply with right hand rule. So that means, as I already said, no last class. So you can keep thumb as x-axis, forefinger as y-axis, and the middle finger would be z-axis. So 2 axis information can brought the 3rd axis information. That is the idea. Okay. And you know that whenever I am actually like putting one body on another body as joints, so how I will actually like accumulate vertically, I will accumulate, right? So that means whenever I see joint parameter, so that means I am seeing the relative information of 2 bodies that would be associated with the joint, but the joint axis would be denoted to z-axis because that is vertical axis. For example, I take 2 mobile phone, I put one mobile phone on top of another. So now the relative information of these 2 can be realized in the vertical axis. But imagine I pinned my, you can say, duster one end, another end I am actually going to connect with another duster. So that means you can see my link is progressing from one joint to another joint in a longitudinal way. So there I can fix x-axis. So then you can see that my link parameter can be realized in x-axis. So that is the idea. The link parameter would be information between two consecutive joints, whereas the joint parameter would be information between two consecutive links. And you can see that they put only two axes can be sufficient. And as per that case, the joint axis always associated with z axis and link, which is always associated with x axis. So that is the idea. And as I already mentioned, the relative position and orientation of two successive links, what you call joint parameter, the relative position and orientation of two successive joints, what you call link parameter. It's quite easy, right? The same logic what we are going to apply. Okay, I already said z-axis is joint relation and x-axis would be the link association. So that is the idea. So these things we can see next. Okay, so that means only 4 parameters are sufficient. These parameters what we call link and joint parameter. For understanding this, I use another PowerPoint. So you can see that I'm taking a link. The link is random link from one of the manipulator I picked. So this link is I-1 link. So since it is I-1 link, so this would be having a joint axis I-1 and I. Okay. So I'm keeping two joints. You can see joint I-1 and joint I. So the joint I'm trying to show as small cylinders. Okay. So you can see that this is the link. This link would be consist of two joints. So joint I-1 and joint I. So what we know that these two would be having axis. So these two axes are associated with z axis. So that means this is zi-1 and this is zi, right? So now you see that if this link is untwisted, that means, so right now you can see that this is almost 90-degree twisted. If I rotate, so the joint I-1 make it, you can say parallel to zi. So that much angle I want to rotate. About which axis? The common normal between these two. So now what I'm going to do, I do a common normal. So this axis to pass through this common normal, I keep it xi-1. Okay. So now you can see that the link parameter always associated with xi-1. So the very first one, rotation about xi-1 to make it zi-1 parallel to zi. Okay. So this is what I call link twist angle, or twist simply called, because if I actually like rotate this much, you can see that these two are parallel. That means the link is parallel. Now I actually like twisting. So it would be having a different orientation. Otherwise, it would be parallel. That's why it's called link twist. So after that, what you can see that this axis and this axis is distance away along x-axis. So this is nothing but physical length of this link. So that's why it's called link length, right? So now you can see that alpha I-1, what is nothing but the angle between zi minus 1 to zi with respect to xi-1 about. So that is what you call alpha I-1, right? So whereas along xi-1, whatever the distance travel, that is what you call link length. Just for understanding, link length cannot be negative because link length is a physical variable, right? That cannot be negative. That means whenever you keep xi-1, you make sure that that would be along with the link progression. Okay. So that is one thing. Now I pick a random joint. So for understanding the joint I picked. So this is associated with two links. So the link I-1 and link I, it is connected. Okay. So now we already know that this link I-1 would be having its own frame and link I would be having its own frame, right? And what else we know? This joint I would be having its own joint axis called Zi, right? So now you can see that xi-1 is here and the xi would be here. Now you can see about Zi. So these two are actually like angle apart and distance apart. This distance, how it look like? It is offset from one plane to another plane, right? It is, that's why it's called joint offset or simply called offset distance. Okay. So it is a joint distance or offset distance or just joint offset. Whereas this angle is the joint angle. the angle between xi minus 1 to xi, okay, is about zi is called joint angle, and the distance between xi minus 1 to xi along zi, what you call offset or joint distance. So now you are clear on this, I hope. Okay. So now you can actually recall the link parameters are nothing but the link twist angle and link length. The link twist angle is angle between zi minus 1 to zi measured about xi minus 1. Whereas the link length is ai minus 1, which is the distance along xi minus 1 to make it the two frames are matching, right? So this is what the case. So you can see that whenever you talk about joint, okay, so the joint would be actually like having a relative information of two links. So that means if I see link parameter, these two joints are fixed, right? So it may be having a rotation, but this link is fixed. That means the link length and twist angle are constants. Okay, so that is the idea. So it's a geometry. The same logic you apply to, you can say, joint parameter. So you can see joint angle is nothing but angle between xi minus 1 to xi about zi. And similarly, joint distance is the distance between or distance along, you can say, zi between xi minus 1 to xi, what you call the joint distance. Here you can see that the Danavitt-Altenberg condition says that so only one motion is possible. For example, if it is a translation joint, the di would be variable. If it is a rotary joint, theta I would be variable. So that means when I try to derive the transformation matrix based on Danavitt-Altenberg, so only one variable, 3 would be, you can say, constant, and the matrix also would be much compact form. So then I can actually like make multiple compact form, and then I can multiply one another, then I will get the base to end transformation. So that is the whole idea. So that is what we are calling DH approach. There is a contradict or conflict approach is there, which is we call screw algebra, which is more abstract. There also only one variable we would be using, that is we call screw wrenches or twisters, but still that is much complicated in terms of algebra, because you need to understand screw algebra. It is little easier if you are familiar with it. You can say the screw algebra and Lie algebra, since not everyone would be convenient with that algebra. So we started talking about Danavitt-Altenberg. I hope now you are clear how the Danavitt-Altenberg approach brought the 6 parameter to 4 and how that 4 parameter described, right? So that is the one important entity you should know. So I hope with that, I'm actually like passing. After that, you know how to find arm matrix, why there are 4 transformations, and how that transformation matrix can be brought, how to find DH parameters, and then how to find forward kinematics using DH parameter, then how to derive the inverse kinematics, all those things you can see it in the textbook or my lecture notes. But now, so I have only 1 hour. I want to actually like move slightly the other set of robotics, which is what we call the locomotion device. So which is we simply call a mobile robot. So as I already said, the mobile robot kinematics is slightly different, right? So what different I said, the transformation of body frame to inertial frame, what we call robot kinematics, but here that would be in velocity to displacement domain. So we want to understand. Already I described, but I will bring it back. So you can assume that the mobile robot like this. Okay. So I am assuming that mobile robot can move only in a plane. Indirectly, you assume that there is a magnetic duster and a steel board. I keep a magnetic duster on the board. So then it would be look like this, right? So now I want to describe the magnetic duster with respect to the board. So then you can see that there are multiple ways to describe which coordinate I need to choose, right? So as I already said, classical mechanics always go with the body center and initial frame. So now I put one corner of the board as the initial frame, which is I'm going to call as a reference frame. And the body also have multiple points. I put the center of gravity or body center as the frame of reference. So now what I am interested, I want to see the position and orientation of the duster with respect to the board. So here the board is represent as I and the duster is represented as B. So indirectly the B position and orientation I'm trying to see with respect to I. So then I can make it. So it would be X displacement, Y displacement and psi angular displacement. So indirectly you can see that so the X, Y, psi are the generalized coordinate in mobile robot, right? So, but you imagine this magnetic duster is connected with some kind of wheel or thruster. Okay. So then the magnetic duster is now like a, you can say, wall climbing robot. This wall climbing robot will have some, you can say, adhesive rollers. Imagine. So there is a wheel here that is trying to move on this white patch. So then what you will get? You will get body fixed instantaneous velocity in forward direction, a lateral direction, and the angular velocity with respect to its own frame. So these all three are instantaneous velocity. At B frame frozen at an instant, and we can realize UVR. Okay. But now what I want to know the information. So this UVR, how it is influenced my XY side, because that is what my interest, my generalized coordinate, how it is varying with respect to time. That is what my interest, how I will do it. So then I can see that either I have to bring it UVR into a positional or displacement domain, but that is not possible because it's instantaneous velocity. What I can do, I can upgrade the generalized coordinate to a derivative of generalized coordinate, and I can map between these two. So that is what I'm trying to do. So indirectly, I'm trying to map x dot in the form of UVR, y dot in the form of UVR, and psi dot in the form of UVR. Since it is a planar, so R would be just psi dot, whereas U and V in the form of x dot y dot or x dot y dot in the form of UV would be consist of, you can say, psi also. That how. So we will take U. So this U would be having two components in I frame, right? So what are the projections? So you take a psi angle. So the U can be projected on xi axis. That would be U cos psi. It can be projected on yi axis. So that would be U sin psi. The same way V can be projected on x and y. So that would be consist of this. So now, for example, you take it the B frame, how it is actually like moving in xi. So that would be x dot. That's supposed to be the vector addition of u cos psi plus, or you can say vector addition of u cos psi and v sin psi, right? That's supposed to be equivalent to x dot. Then only it would be equivalent, right? The same way, the y dot supposed to be equivalent of vector addition of these two red. So that is what we are actually putting it. This is the vector addition. This would be x dot. This vector addition would be y dot. So now I can write x dot in the form of, you can say, u and v, and y dot in the form of u and v, and psi dot in the form of uvr. So in this case, it is a planar, just r, right? So now you can see that I brought the relation. So x dot, y dot, psi dot in the form of uvr. I'm trying to make it that in a matrix form. Okay. So this matrix is again a transformation matrix, but it is mapping, you can say, the body fixed velocity to earth fixed velocity. It is a mapping tool. This is in the differentiation domain. This is more like, you can say, vector differentiation with respect to vector, that form. So this logic brought by Jacobi. So that's why it's called Jacobian matrix. So now you can see that this matrix brought it as a Jacobian matrix. So now the zeta is nothing but UVR, which is nothing body fixed velocity. In our understanding, it's we call input velocity commands. Whereas this x dot, y dot, psi dot is the generalized time derivative or time derivative of generalized coordinate, which is earth fixed velocities. So now this mapping, what we call mobile robot kinematics. Now the zeta can be brought in terms of, for example, you are taking a surface vehicle in underwater or water, then that would be with the consist of thrusters. So the zeta would be in the form of thruster velocities. For example, if it is a mobile robot, the zeta would be function of, you can say, your angular velocity of the wheel, or you can say angular velocity of the motor. But the generalized form is, so eta dot in the form of J of psi into zeta. So this is what we call mobile robot kinematics. So you can see this is mapping between these two. So now in this case, if I know the velocity command, indirectly I take a mobile robot, I know individual wheel velocities. Okay. So indirectly I know that how much forward instantaneous velocity, what would be the lateral instantaneous velocity and instantaneous angular velocity with respect to z-axis known. I try to find out what would be the time derivative of generalized coordinate. This is what we call forward differential kinematics. So indirectly what we say, for given velocity input command, finding derivative of generalized coordinate. So indirectly finding system motion. So this is like this. So this is more like you take a real robot, put your motor and run it, right? You are simulating or analyzing. So that's why it is called simulating or analyzing the system in velocity level. So which is we call forward differential kinematics. Whereas the inverse differential kinematics, so for given eta desired dot, we are trying to find out what would be the zeta. Okay. So then you take a J inverse, right? So that is what we are trying to do for given desired derivative of generalized coordinate. Okay. Or in simple sense, given position trajectory, finding the corresponding velocity input command. Indirectly, try to follow a given trajectory. What would be the control inputs? So this is more like a controlling the problem in, you can say, velocity level, that to open loop control. This is what we call inverse differential kinematics. I hope now you are clear about these two, right? So what you clear? So you know why transformation matrix we have used. So why we have come with robot kinematics, how the robot kinematics is actually like differ from mobile robot to manipulator. So manipulator forward kinematics and inverse kinematics is mapping between, so task space to joint space or joint space to task space. Whereas mobile robot kinematics, manipulator kinematics like this. Whereas mobile robot kinematics is the other way around. It is mapping between, you can say, body fixed to earth fixed frame reference. So that is the understanding. Okay. So that is the understanding. So in that sense, so it is, you must be clear up to kinematics level. So if time permits, we will do the dynamics later. Right now, I will just show our own research so that you will get a clarity what way we are all working and what challenges we are doing it. So in that sense, so you know that I am not a theoretician, I am experimentalist. So I started doing this research since my BTech. So I had opportunity to work with different defense projects, and then I started working with my own center. So now I have own lab. Okay. So our lab, when I was in Indore, so I was having a center called robotics and control. Here also we have Center for Robotics and Control, but I have a small lab called Service Assistive Field and Exploration Robots Lab or Robotics Lab. So this is, we simply call SAFE. So here we do conventional and non-conventional system. Just for understanding your interest, so I put it the non-conventional stuff here. So you can see that, so instead of a traditional wheel, we have a star, which is a 5-spoke model. So which can actually like maneuver in a rough terrain or even in a stack climbing. The same way the wheel with the leg. So instead of conventional wheel, it is having a, you can say, legged connected. That leg also can be controllable actively or passively. This can give a suspension, and as well as it can provide manipulability, or you can say manipulation with respect to obstacles or the terrain. Then you can say negotiation between the terrain. So you can see that this is commanded autonomously to go the stop and come down. So it is taking its own time to navigate to reach the target. So you can see that when it is going, so it is having some disturbance, or it is not able to move up. So it is negotiating. Sometimes it is not negotiable. So it is trying to take different path and trying to go up. So this is something like non-conventional robots, which we usually work. And you can see that how it is actually like climbing, and you can actually like see how it is actually like coming down very stable. That is what we have seen. Okay. So now this is one part. The same way we do work with agriculture and underwater. So you can see that this is one of the agriculture robot, but this particular robot we have developed for many other purpose, even the space rover challenge, or you can see all-terrain vehicle challenge, or simply a agriculture robot. These all we have tried. So on top of this, we have a manipulator also, but this is the initial testing when we were tried to see the terrain adaptability. So you can see that this is one other thing. The same thing when we were trying for something like a defense project where we need to handle ammunition in their inventory, but the same robot, before we tested for ammunition handling, we tried to see that can we use this robot for large fruit or vegetable harvesting. Here you can see that the low-key handling is done with this. So it's look like slow because we have taken very small step so that we can see that so whether it is doing properly or not. The same scenario we have tried for underwater robots also. So there are two type of underwater robot we used to work. So one is actually like for observation in a very bio-inspired like a fish kind of robot, and the other one is actually like with a manipulator for intervention task. So you can see that both manipulator and just biofish. So these two systems were currently commercially available. So Oceanotics is the company which is selling it. So if anybody interested, you can actually like reach them. But these two robots tested in front of the stakeholders, and then finally we transferred. Even the NIOT defense people and NSTL people all were tested this, and then we have tested even a sea state too, and then transferred to the technology to the startup. And the same scenario, if you look at it, so I always insist our student to come up with some kind of product development, because India is lacking in product development. We always see that India is a potential, you can say, commercial business entity. But when we look at it in Indian perspective, we don't have number of products by our own. So in that sense, we need to encourage product development as one of the critical. So then only our, you can say, economy can grow. So in that perspective, I always insist whether it's a BTech student or PhD student, they would be finally ending with some product, but PhD student will do rigorous research, come product development. BTech students will definitely end up with product. For example, this is a railway track, specifically next to the platform cleaning robot, and this is a multi-modular system. It can fly and crawl, and this is a fruit harvesting robot. So this is, you can say, a small pruning tool like this, and this is actually like a small you call omnidirectional robot specifically for warehouse. Like that, this is we have developed this rehabilitation robot. Like that, we have developed multiple uh, directions. So that way we have seen. So I just want to give some specific point, since it's a broader topic. I just want to give an address. So how the robots are evolved and why we need to understand the mechanics. So that is the perspective. You all know like how the industry evolved, right? So I don't need to explain that because industry 4.0, you are all clear. But my interest is when the industry 1.0 has come, mechanization happened, right? Then mass production happened by electrification. Then the magic happened because the semiconductor industry boomed. Automation has come. Automation did not come alone. It came with a manipulator, right? That is the change. Then what really in the industry 4.0 brought, and why he brought, you may be knowing, but what it brought, so it is a cyber physical, that is one advantage. So apart from that, what the robotic perspective, so we are all, you can say, have both capability in a robot aspect. What that means, we have our own locomotion. That means we can mobilize ourselves, and as well as we can manipulate objects around, right? But in industry 3.0, mostly the robots are actually like one end fixed. That means it's a manipulator. It cannot have a mobilization. Even if it is a mobilization, that would be very limited, like AGVs. But what we are envisioned in industry 4.0 is more like AMR. That too, you can say teleop, or you can say cyber connected AMRs. So that is the idea. You can see mobile manipulator is the critical thing. when you put that into a case where we are leading to the community where the super smart. So that means we are thinking about the industry 5.0, that would be human center. That means earlier it was digitalization. So you can see like the automation and then digitalization. The digitalization now even furthermore, it's actually like customization, or you can say human center. So that where we are actually like dealing it. So that means our robot should be more, you can say, intelligent, and it should have all capability. So if you put that capability, it is actually like very, very different task. So I'll just put it what we are thinking at. So in the basic entity, when it is 60 to 70, even the 71, the first, or even 61, very preliminary prototype has come, and 71 somewhat full-fledged prototype has come. The roboticians were working in the past to even now two broader themes. One is to fulfill the human life indirectly activities on daily life. So any human being, their living life should not be harmful. In the sense, their comfort should be primemost. Here, the money is not the problem. The compromising money is not the concern. So that means this is a human center. So that is one primary objective people were working. The other objective is to fulfill this comfort is activity on daily living, right? On top of that, their food, their, you can say, device, their bed, everything need to be produced, right? The demand keep increasing, right? So in that sense, the productivity base, the machine base, the economic base, efficiency base, we need to see. So that is the industrial robot. One is actually human oriented, the other one is machine oriented. These two directions people were working. You might be laughing when you would have seen in the news. So Japanese made eye winking robot, Korean make smiling robot, and German made talking robot. So why these people are doing some crazy stuff? But this is important, right? Whenever we go abroad, what we always do, we raise our collar, say that we have largest youth population. But imagine 10 years down the line, what we would be having more middle and elderly people. But our community has changed, right? And our society also changed. Earlier, we had a joint family. Now it is a nuclear family. Even this nuclear family is doing much more nuclear. So I have an example. I think Mayur may be easily interpret. So one of our faculty had a, you can say, family like this. His wife was working in US, so, and his son was studying in Hyderabad. So these all three meet once in a year in the summer vacation. Imagine this is the life. So if that is the case, so you need a companion. In the olden days, we had a pet animal at least to give some kind of, you can say, companion. But now lots of gated community has come, and the residential complex, they clearly say no pets allowed. So that means, so you need a companion robot, at least replacing the pet. So that means you should have a dog like robot, cat like robot, or fish like robot, or just emotional therapy robot. So that should be there at least. So that should be very intelligent, right? For example, you take a dog, the dog should whatever does that same thing, or at least close to that, the dog robot should do, then only the companion is there. So what indirectly we are saying that we are thinking about a human friendly companion robot. The other side is the smart industrial robot. Just for understanding what smart industrial robot, imagine a power plant inspection or power plant condition monitoring. Every 30 minutes or every 1 hour, you need to inspect, and then you have to take a call. Now imagine human is doing, there may be prone to be error. So now this robot is actually like taking the reading of individual valve, individual knob, individual gauge, right? So immediately it process and then send it to the control station. For example, now you can see that the pressure reading may be low or the current rating is low. So it sends that, okay, this valve is actually like open, might be. Okay, it command another robot, hey, you see pressure is reduced, you go and open the valve. So now the another mobile base with the manipulator is actually coming and it is opening the valve. So this way you can see that the system is actually like relieved from the fatigue and complex task. So immediately some people may jump that, sir, why can't we do this way? So why can't we implement industry 4.0? The idea is IoT. So IIoT, that is there, but that would be very cost expensive. than compared to using multiple robots. Each and every valve, each and every knob, each and every motor you connected with the network, the networks are supposed to be heavy, right? And accessible. In addition to that, the cost of each industrialization, or you can say each IoT enabled, that will always lead cost, right? So that's why people prefer this kind of scenario. So that means both end mobile manipulator with the intelligent what we wanted. So that make the robotician is far away from the current scenario. So that is what I just wanted to tell. So in that sense, you can see that even the warehouse handling, or you can see the industry how envisioned. So this is the envisioned industry, and you can see this is the real industry. You can see like almost it is very similar, right? So this is, you can see everything is operated by robot, and here also you can see several mobile manipulator, and these are all AM machines, and you can see like this is warehouse. So here the shelf is carrying, and here two manipulator is handling the shelf, and then the picking which objects need to be done. So these are the modern industry, how the manipulator or how the, you can see, mobile bases are using, what end, what extent these all using, you can see, right? So that is the understanding or idea which I thought of putting into this and this particular forum. So that means what we are seeing it, the robots are very smart. So that means it is simplified and collaborating with the human or machine, and finally it is digitalized. So that means robots are getting smarter and smarter, and robot collaborate with workers. When the robot has come, it is like a wild animal. It put it in a cage. Later on, it thought that you share the workspace, but I will not intervene. You will also should not intervene. Then I said, I'll put one part, you put one part, but we should not collide each other. Then they say, okay, I'll hold, you punch, or you hold, I will punch, like that cooperation. But right now, what we are looking at responsive, even if I'm not putting object, hey, put it, that kind of commanding. So this is what we are seeing, the collaborative. For example, this lady did not take the hand, but the robot is not harming. But imagine if it is a conventional robot like olden days, it would have penetrated her arm or injured her arm. So that is what we are seeing it. So this is what we are looking at. So that means, so that scenario, the robot collaboration is keep evolving. There you need to know the mechanics. We need to know the dynamics. These are all important. That means the robots evolved from manipulator to mobile based with manipulator, and then completely mobile based with articulated to anthropomorphic. And where we are currently here, you can see that this to this. So this is a cable connected, but here cable is not there. But what you notice that one leg is you can say stable, then the next motion is happening. But here you can look at it. This is what we are envisioning. So the dynamic walking. So you can see that this foot is about to touch the toe is, or you can see heel is touching, the toe is rising. So whereas here you can see that it is firmly fixed. It's a static walking, but what we wanted is dynamic walking. This is what the bigger challenge, not completely achieved. Even the Boston Dynamics still testing. That is where the standing. Okay. So that is what I want to say. There are multiple challenges. So the challenge is actually like from, so the metallurgist to even a humanities engineer or humanities, you can say writer, everything is going because ethics is not defined, materials is not found for all the challenges. So that means the challenge is quite open. So with that, I'm just stopping at right now. So you can ask any questions related to this. What we are actually like envision. So like this, for example, group of ants, how it carry a, you can say vada or probably sugar. The same way here, these all independent. It is not connected with one to another. It is independently. It is pushing this box. How the ants will carry, like that. So that is what the idea here. So that is what we are also looking at. So that is the way I close this particular session. So you can ask question now.
Thank you very much, sir. Participants, is there any questions? Participants, is there any questions from your side? Okay.
No, sir.
Okay, sir. Yeah, I think there is one question. No. Sir,
And
sir, there's no
yeah,
question. Yes.
so, and if you want to know more about mechanics, there are multiple courses are there in NPTEL and other forum. Even my own course is there in NPTEL, both mechanics and control of robotic manipulator and wheeled mobile robot. It comes in alternate semester. So these two courses are very much connected with your own realization. If you understand this course, you can code yourself in Python or MATLAB, and then you can realize this. So once you are convenient, you can start developing your own robot and test it. So I'm not promoting my course, but these two courses are useful. And if you want, you can actually like look into NPTEL and then take this.
Thank you, sir. Thank you very much, Dr. Shantakumar Mohan, for sharing your valuable insights and rich experience with us today. And sir, your session was truly informative and inspiring, giving us a deeper understanding of advancement in robotics field. So, on the behalf of organizing team and all participants, we express our sincere gratitude for taking the time to be with us and making this FDP session to be meaningful. So, thank you once again, sir. We look forward, sir, to more such an enlightening interaction in the future, sir. Thank you. Thank you very much, sir.
So thank you all of you. Thank you. See you then. Bye.
Thank you, sir.